Jayavardhan, what is the problem exactly? Please refresh your screen. Please refresh, cut and paste one more time. While Jayavardhan is attempting to connect to the screen, I have an announcement. So you had physics as your next class. We won't be having that class, just so that we don't start a new topic right before the break. All right, so we'll reconvene sometime after the break for the physics class. All right, did you all get that? Okay, very good. Let's start off. Here we go. So today we're going to look at roots of polynomials or zeros of polynomials and what that means. Here we go. So here's the applet which comes up when you open it, and I just showed you that, and you should be able to see. This is on your, I'm on the class screen now, yeah? I'm not on the applet screen, I'm on the class screen. But I guess you can see that. I don't think you can see that. You'll have to go back to the class. I'll tell you which screen I'm on. Alright, so this is the applet that you should have been able to see. Yeah? And essentially what I need to explain, really the only thing I need to explain is what these values here are. As you can see, you've got a whole bunch of values, A0, A1, A2, A3 up to A5. What do these values really mean is what I need to explain. The rest we can see on the experiment screen itself. Okay, so essentially if you had a polynomial of this kind, okay, px is a0, which can be written as a0 into x raised to power 0 plus a1 into x raised to power 1, a2 x raised to power 2 plus a3 x raised to power 3, and so on up to a5 x raised to power 5. Right, that's the polynomial. These a0 to a5 are called the coefficients of the polynomial, and that's what those values on the screen are. Alright, on the virtual experiment screen are. These are the allowed ranges in this experiment. And so when we give this to you as part of the post-lab quiz, please feel free to play around with the experiment and adjust the settings as you to different values and see what happens. I will take you through some of them today, but it's obviously not possible for me to do all of them. Okay? Alright, the first thing really is this, and I'm going to the virtual experiment now. Can you please switch your screen to the virtual experiment? Okay, so this this experiment is pretty nifty. It does a few things automatically. So what it does is it is automatically able to detect the degree of the polynomial. Now what is the degree of the polynomial? The degree of the polynomial is the highest power of x that is present in the polynomial. Now you might say that, hey, I saw everything from x raised to power 0 to x raised to power 5, so why isn't it always a degree 5 polynomial? If you set a5, which is the coefficient of x raised to power 5, if you set that to 0, then the value of x doesn't matter, right? For that fifth order term, and it's going to be, the fact that it's x raised to 5 doesn't matter because it's always multiplied by 0. Do we agree with that? And therefore that makes it, instead of a fifth order polynomial, that actually makes it a fourth order polynomial. Yes? So this experiment is able to detect what order polynomial it is. It does this in two ways. The first is you see the color of this graph. This varies depending on what is the order of the polynomial, and you can see the degree over here. On the screen itself, you should be able to see the degree. It's able to detect this on its own, which is quite a nifty thing. And we'll see how this happens as we go. Okay, the next thing this thing is able to do is to figure out zeros of a polynomial. Now, what are zeros of a polynomial? You should, something you should understand already. Here's a polynomial expression, a0 into x raised to power 0 plus a1 x raised to power 1 plus a2 into x raised to power 2 and so on up to a5 x raised to power 5. If I set it to 0, then I'm saying that this is the condition that must be satisfied. In a sense, that is now an equation that needs to be solved. Do we agree with that? And so this experiment is kind of smart enough to be able to figure out what is the solution to such an equation. All right? As a very quick example, as you can see, this is a fifth order polynomial. So if you set a0 equal to 1, a1 equal to -1, a2 equal to -4, and so on and so forth, as listed on the top left, then and set that to 0 and solve for what values of x will that polynomial be expression be 0. Turns out that these are all the values. Can you see these? n1, n2, n3, n4, n5. Can you see these? These represent the values for which that polynomial expression is 0. They're also called the zeros of a polynomial. Is this clear? What these values are? Now it's n because it's a fifth degree. If you do a fourth degree, then you get r's. You'll get r1, r2, r3, r. So okay, this is a fifth degree polynomial. It has 5 roots. Can you see that? Or it has 5 zeros. A fourth degree polynomial will have 4 zeros. A third degree polynomial will have 3 zeros. A second degree, which is a quadratic, will have 2 zeros. And a linear polynomial, which is simply x raised to power 1, will have simply 1 zero. And we'll see that as we go. The only point I want you to note is that while it's written as n1 to n5 here, it'll be different. It'll be r1 to r4 for fourth degree, c1 to c3 for third degree, q1 and q2 for second degree, and just l for degree 1. Okay? What are the zeros of a polynomial of degree 0? Any thoughts? The polynomial itself. So I guess it's a little difficult to say this simply because you could look at it in many different ways, right? So if you ask the question, it depends on how the question is asked. If you ask the question, what is a polynomial of degree 0? It's like fx equal to 5. Yes? Do you agree with that? That's a polynomial of degree 0. Fx equal to 5. Yeah? What values of x satisfy this equation? One value. Really? 5 values. How many values if x equal to 1? Alright? What is the value of fx? fx equal to 5. If x equal to 1, the value of fx is still 5, right? If x equal to 2, what is the value of fx? 5. If x equal to 3, what is the value of fx? Still 5, which means that it's true for every value of x, right or no? Can it ever be 0? Can the polynomial expression ever be 0 for any value of x? If fx equal to 5, for any value of x, can the polynomial be 0? No, it can't, which means that there are no roots. Okay? What if fx itself was equal to 0? Instead of fx equal to 5, if fx itself was 0, then is the polynomial 0 for x equal to 1? What's the value of fx for x equal to 1 if fx is 0? Anything. Okay, let's take it one question by one question. Okay, the question I'm asking, fx equal to 0. This is the polynomial, which can be written as fx equal to 0 into x raised to power of 0. What is the value of 0 into x raised to power of 0 when x equal to 1? Zero into 1 raised to power 0 is 0. What about if x equals 2? What is the value of 0 into 2 raised to power 0? 0, exactly. What is 0 into 3 raised to power 0? Still 0. Isn't every value of x, every real value of x, a solution to this polynomial? Which is why I said it depends on how the question, on what exactly the question is. Is this idea clear? So it can get a bit confusing if you don't go through the details, yeah? So you can't just say 0 offhand, it depends on what the polynomial itself is. Okay, alright, now that we understand that, let us quickly try, can you go back to the class please? Okay. Alright, here at the class screen, I'm just going to flip through to a little bit of an exploration. These are just instructions on how to use it, which of course we'll post for you. Let's look at the function fx equals 5x plus 7. Are you all on the class screen? Can you see this slide on the class screen? Okay, very good. So this is our function fx equal to 5x plus 7. We want to find its zeros. What do? We have to set this expression to 0. So we set 5x plus 7 equal to 0, and if we solve, this is pretty simple, we get x equals minus 7 by 5. Do we agree with this? Which is about minus 1.4. Alright, let's look at how we use this tool or this experiment to try and figure this out. Let's set up the polynomial first. The original polynomial was 5x plus 7, which means a0 has a value of 7. Okay, then a1 must have a value of 5. Okay, there we go. And all the other a's must be 0. As you can see, you need to go back to the experiment. I'm sorry I didn't mention that. Please go back to the experiment and look at what I'm doing. Can you see that I have set a0 equal to 7 because that's the coefficient of the term x raised to power 0. I have set a1 to 5 because that is the coefficient of x raised to power 1. I have set a2 to 0 because that is the coefficient of x squared. a3 to 0, that's the coefficient of x cubed, and so on and so forth, because my expression is simply 5x plus 7. Do you realize where I get all these values from? Why my slider settings are where they are? Is this clear? Okay, I want you to look at two things. First, remember I said this experiment is smart enough to detect the order of the polynomial or the degree of the polynomial, and you can see in the text in the top right that it is a linear polynomial with degree 1. Do we agree with this, what the experiment is saying from our knowledge? Okay, can you see that the color was when it was an order 5 polynomial, the color was pink. Now can you see it's like, I don't know, some orange color? Yes? That's the other way it tells you what is the order of the polynomial. Okay, what the degree of the polynomial is by changing the color of the graph itself. Now we just found the 0 of this polynomial. And if you remember, it was minus 7 by 5. It's approximately minus 1.4, or well, exactly minus 1.4. Do we agree that this is the value over here? That's where this L is pointing. That is the 0 of the polynomial. Okay, why is this the 0 of the polynomial? Remember, this is nothing but a graph of the polynomial, this orange line. Okay, as x varies, how does the polynomial itself vary? And the zeros are the value of x for which the polynomial takes a value of 0. Do we agree that at this point, when x is minus 7 by 5, fx, which is 5x plus 7, which was the polynomial, has a value of 0? Do we agree with that? And hopefully this gives you a sense for what it means to find the zeros of a polynomial. Alright? Okay. So this was pretty straightforward, not too difficult. Just one moment. Let me see if I can actually zoom in for you. Yes, I can. Can you see that this value is about minus 1.4? It's just to the right of minus 1.5. So about minus 1.4. Yes? Okay, very good. That was simple. Let's go back to the class screen, please. Now we take a look at the next order polynomial. Okay, which is, we are now looking at a quadratic polynomial. Fx is given by 2x squared minus 7x plus 6. Do we agree that the highest order of x, or the highest power of x, is 2? Yes? And therefore this is a quadratic polynomial. We want to find its zeros. What do? We set the polynomial expression to 0. Now, have you been taught how to solve for a quadratic? Yeah, minus b plus minus, etc., etc., the whole formula. Okay, so if you actually do that, then you will get these two values, x equals 3 by 2 and x equals 2. You can substitute them back in here and see that it's actually true if you wish, but do that after we finish this class. Let's evaluate whether our experiment is able to get this right or no. Okay, so far we know how to do these solutions, so we are kind of cross-checking whether this experiment works or doesn't work. Let's go back. What values do we need? The expression is 2x squared minus 7x plus 6. So in this case, the value of a0 ought to be 6. Value of a1 ought to be minus 7. Okay, it's a bit delicate. So be pretty careful. Alright, I've got that right. a2, which is the coefficient of x squared, must equal to oops, I think I need a more sensitive mouse, or maybe a less sensitive mouse. Ah, phew, finally. Okay, and the other three must be 0. Do we agree with this? Okay, very good. Let's look at the roots. It's a quadratic polynomial. We should have 2 roots. Okay? Isn't that what the 2 roots, as we said, should be x equals 3 by 2, which is 1.5, and x equals 2, which is just over here. Let me zoom in. And there. Do you agree that it's correctly solved for the roots? Also, do you agree that it has detected the degree of the polynomial correctly as 2 and has colored it differently now in green instead of orange? Alright, very good. Okay, now let's take a look at a 3rd degree polynomial, which is going to be, here's what I'm going to do. I'm going to set it for you here. Yeah, and my equation is going to be 3x squared minus, well, not a 3rd degree, it's a 2nd degree polynomial. It's going to be 3x squared minus 8x plus 6. Alright? So, which means that x still equals 6, I'm sorry, a0 still equals 6, a1 must be minus 8, and a2, since it's 3x squared, a2 must be 3. Oh, sorry, there we go. Okay, let me zoom in. Now this is a 2nd order polynomial of degree 2, and we expect it to have 2 roots. We expect it to have 2 zeros. We just solved one previously where we got 2 zeros, but we're not getting any zeros here. Let me actually zoom in even more, or zoom out even more. And you can see that this graph actually never gets down to a value of 0. The polynomial never takes a value of 0. Why is this? Isn't this a paradox? We just saw that it should have 2 roots, but now we're not seeing any roots here. Why? Okay, very good. Very good. So the issue here is that if you actually try and solve this quadratic, which is 3x squared minus 8x plus 6, you'll find that you do not get real roots. Is this clear? And therefore, how do you graph something that's imaginary? It's a little difficult, right? Something that's not real, it's kind of not possible. And therefore, this experiment fails as a result of that. Is this clear or not clear? Okay, very good. So far we now, we've done a bunch of experiments, and we see that, okay, this thing seems to work. Yeah, this thing kind of seems all right. It seems to work. Let's try and test it some more. What if we have to solve, please go back to the class. What if we have to solve an equation, or find the zeros of a polynomial of something like this? X raised to power 5 plus 2x raised to power 4 minus 21x cubed minus 38x squared plus 80x plus 96. We set this equal to 0. Is it an easy thing to solve for this? Is it even remotely easy to solve for this? No, it isn't, right? And to find the zeros of such a polynomial, really difficult. But hey, let's put our faith in this experiment. We've tested it for lower order polynomials. We put our faith in it, and we hope that it works. And of course it does, yeah? Otherwise I wouldn't be teaching you this stuff. Alright, let's use our experiment, which we now know does indeed work, and we will solve for the zeros using the experiment instead of trying to do it manually as we have been doing so far. Right, so what are the values? Go back to the experiment, please. So it's x raised to power 5, which means a raised to power 5 must be 1. And so I set this to 1. 2x raised to power 4, which means a4 has a value of 2, and I set it there. Minus 21x cubed is the next term, so a3 has a value of minus 21. There we go. It's minus 38x squared, correct? So that means that a2 has a value of minus 38. All right, here we go. I set it to there we are. It's 80x is the next term, which means a1 has a value of plus 80. Yeah, there we go. And finally it's plus 96, so a0 has a value of plus 96, which I am going to put here. Okay, so this is what you get, and we can't really see this, right? So it's a pretty crazy looking graph, so we need to zoom out a little bit. Remember, to zoom out, you hold the shift key down and use your scroll wheel on your mouse. Okay, and that's what I'm doing. I'm zooming out. And there we go. And this is still looking a bit weird, but slightly better than earlier at any rate. Okay, we are interested in the roots, so I'm just going to try and zoom it so we can see the roots clearly. As you can see, it's come back to an order. It's come back to. Okay, let me just. Alright, so that's a slightly better looking graph. So I've basically, all I've done is I've tried to zoom so if you right click you can zoom the axis and you can set the ratio of the x-axis to the y-axis. Okay, and I have taken a 1:, let's take one of these ratios, 1:100, that's too much. Let's take this as 1:50, that should serve our purpose, or 1:20 perhaps. No, I think 1:50 is the right ratio. Okay, that gives us a good sense of what the graph looks like. Yes, do you agree with this? Again, remember, shift and drag if you want to move the graph around, shift and scroll wheel if you want to zoom. Okay, those are the controls. All right, as you can see, there are 5 real roots: n1, n2, n3, n4, n5. These are the 5 real roots, and you can they're written as n because that's what the experiment uses to show roots of a 5th degree polynomial. Alright, is this clear now? What have we discussed? What have we really studied in this experiment? We studied what are roots of a polynomial. Essentially, they're those values of x for which the polynomial itself takes a value of 0. Okay, we've studied the idea that polynomials could have real roots or imaginary roots, and we saw how in some cases there were imaginary roots which did not show up in our experiment here because it's capable of only tracking real roots. Alright, we've come to the general conclusion, although we didn't see it specifically for imaginary roots, that a first order equation or a first order polynomial will have 1 0, a second order polynomial will have 2 zeros, a third order will have 3 zeros, and so on and so forth. We discussed the idea of simply a 0 order polynomial and what the zeros of that might be. And that's pretty much it. That's been our focus of today's lab. Is everything clear here, or is something not clear from what I've explained?